Hello everyone, I am Samunath Mantal and I welcome you all in my channel Mission MBBS. Here we go. Today we are going to talk about units and measurement. This is our first chapter and mainly we are going to focus today on dimensions. Before going to dimensions, there are a few terms that need to know. These are very easy. We have been studying this from our earlier classes like 8, 9, 10. So we'll just see it once, go through it once, and then we will discuss about our dimension. So let's get started. So here you can see, first we are going to talk about physical quantity. What are physical quantity? So the quantity which can be measured, simply the quantity which can be measured are called physical quantity. If we can measure something, then that is the physical quantity, and if we cannot measure something, that's not physical quantity. So anything that can be measured by using instrument and that describes the law of physical world are called physical quantities. Here we have one expression for physical quantity, n into u. For example, if I write here I have a pocket of salt which is suppose 1 kg. I write it 1 kg. So here 1 is what? It's the numerical value, n, numerical value. And this kg is its unit. Its unit. So these two makes up the physical quantity. This describes the object that we have, that is 1 pocket of salt. How many pocket of salt? 1 pocket of salt. And what is its amount? That is 1 kg. So it describes the object. So this is physical quantity. It can be measured. It is measured, right? N into u, this numerical value into unit. Numerical value into unit. This is physical quantity. Alright. So here we have 3 type of physical quantities: fundamental physical quantity, derived physical quantity, and supplementary physical quantity. Let's talk about fundamental physical quantity. So those physical quantity which do not depend on any other physical quantity, which are independent, which are the base for other quantity, they are called fundamental physical quantity. There are altogether 7 fundamental quantities, fundamental physical quantities in SI system. SI system also known as System International D unit. So they are length, mass, time, temperature, electric current, luminous intensity, amount of substance. See, their SI units are here: meter for length, kilogram per mass. Actually, in ancient time, there were no SI unit which were well accepted. Different people used to use different unit for measurement. Some used to use hath, bita, steps, which were not uniform in all conditions. With the advancement of science and technology and growing communications, they felt the need of a common unit, and then different unit came into existence. You might have studied about CGS system, FPS system, foot pound and second, similarly MKS system, and finally we got the SI unit, SI system of measurement. So these are the SI unit: meter, kilogram, second, Kelvin, ampere, candela, mole. These are the SI unit. So let's proceed ahead. Now we have derived physical quantity. Derived physical quantity, as the name suggests, derived from what? Fundamental quantity. Fundamental quantity, I said, it is the base quantity, base physical quantity. So derived quantity is those which is derived, which is made up of fundamental physical quantity. For example, if we take the example of force, so here force, see, force, it is mass and into acceleration, isn't it? Here mass we can measure in terms of kg and acceleration it's meter per second square, isn't it? So here we have mass m, isn't it? It's meter, it's length, and yes, second, it's time. So we have three fundamental physical quantity used here. See, mass, length, and time, which make up of derived quantity, that is force. So hence it is called derived physical quantity, which is made up of from fundamental physical quantities. Are you clear? So next we have supplementary physical quantity. Supplementary physical quantity we have two, that is plane angle and solid angle. Plane angle is radian unit and solid angle is steradian. Now the main topic, dimensions. Now let's talk about dimensions. Dimensions are the power to which the fundamental unit are raised in order to express the derived unit of a quantity. Dimensions are nothing but a power of fundamental quantity which is raised in of the fundamental quantities in order to express the derived unit of a quantity. How many times of fundamental quantity is a derived unit that is expressed by dimensions. You may not be clear, let me explain it by an example. For example, here I'll take the example of area, isn't it? So area we write meter square. Here it is made up of length 2 times the length, isn't it? So it's not independent on its own. It is made up of fundamental quantity, that is length. So it is a derived quantity, it is made up of fundamental quantity. Now that is we have already talked about it. So dimension, here length, the fundamental quantity used here is length. I have said dimension are the power to which the fundamental unit are raised in order to express the derived unit of the quantity. So this, let's write this fundamental quantity and power of this fundamental quantity inside this big bracket. This is a dimension of area. Now here see, we write this in terms of ml and t. This is the trend we use. We write it simply in terms of ml and t, mass, length, and time. Here is no mass, so m to the power 0, length 2 times length, and time there is no unit of time, so time also 0. So this is what is called dimension of area. Here see, this fundamental unit, fundamental quantity units are there. Fundamental quantity is there, mass, length, and time, and the power raised in of this fundamental quantity, and inside the big bracket represent the dimension of the derived quantity. So this is what we call dimension. Now let's take another example, volume. Here we see volume is meter cube, 3 times the L. So we simply write M0 L3 T0. This is the dimension of volume. Now let's take another example, density. Density, isn't it? So density, here we have mass by volume. Mass we measure in terms of kg and volume in terms of meter cube, isn't it? So here for kg we write mass m1, and for m cube we write l cube. Meter is the unit of length, so l cube, isn't it? So this becomes m to the power 1, l to the power 3. There is no dimension of time here, so t 0. This is the dimension of density. Let's take another example. For example, acceleration. acceleration. Acceleration, it's change in velocity by change in time. Change in velocity by change in time, isn't it? Change in velocity by change in time. So here it's meter per second into second. So second into second. So it will be length by time square. So this will become m. There is no kg, no unit of kg mass. So we write m to the power 0. Here is 1 unit of length. So L to the power 0. Let's take another example of acceleration. It's change in velocity by change in time. It will become meter per second into second. So for meter we write length, and for second it's t to the power 2. There is 2 seconds, so 2 times the temperature time. Let's take another example. For example, acceleration. So acceleration is change in velocity by change in time. It is meter per second into second. So that is for meter L, and for second there is 2 seconds, so 2 to the power 2. So m0, there is L, there is 1 L, so it will be 1. It will be 1, and there is 2t, so it will be t minus 2. It will go up, it will be minus. So that's the dimension of acceleration, isn't it? Well, keep these in mind. You should keep this in mind. This will help you later while solving the complex one. Keep this in mind. Repeat it for 5 to 10 times. It will be set up in your mind, and this will help you later while you will solve some complex one. It will help you. We'll see complex one too. There we'll use this. So keep this in mind. Let's take another example. This force. See, force. So force, it's mass into acceleration. M into a mass into acceleration. There we write, for mass we write kg, for acceleration meter per second square, isn't it? So here what becomes? For kg mass to the power 0, not 1, mass to the power 1, there is 1 kg. So for length also 1 power. For second minus 2, it's in divided form, so when it goes up it becomes minus 2. So this is the dimensional formula of force. Okay, so in this way we write the dimensional formula. I hope you are clear with this example. Now let's see ahead. Here I have made a complete list of all the dimensional formula. These are very simple, when you will complete all the physics, reading of all the physics, when we are clear about all the formulas, when they are by heart to you, then these are nothing. These you can work out in a second. You can make all the dimension formula, but first you need to know all the formulas. So you can go through it, take a screenshot, and you can go through it. Now let's see one dimensionless physical quantity, strain. Here I will take example of strain. Strain, it's change in length by original length. So both are meter and meter. Both will get cancelled. See, both fundamental quantity will be length. Both will be cancelled here. What we get is m to the power 0, L to the power 0, t to the power 0, isn't it? So for all we get power 0. So this is a dimensionless. It has no dimension. Let's take another example. Till now we have only written in terms of m, L and t, but sometimes we get a condition of dimension where we get to see ampere used, A. Similarly mLTA. Sometimes we get K also in terms of temperature. So let's take another example where we get mLT and A also. So see here one example. capacitance. Here C, capacitance C equals to Q upon V, charge upon volume, voltage, potential difference, charge upon potential difference. So here we'll get Q, current into time, upon this voltage. We can write work done upon charge. So it will be IT by this work done. We can write force into displacement, and this will become IT. Q, it will go up. We can write IT, isn't it? For Q, in place of Q, we can write IT. Now I had said you to remember the dimensional formula of force. It will come into use here. M into A, mass into acceleration, into displacement, into IT, isn't it? For I, you will write its current, so it will write ampere A. For time, you will write T. For again current, will write ampere. For time, will write T. This is mass. For mass, will write M. This is meter per second square, isn't it? Acceleration. So for meter, will write L. For second square, T. It will go up, it will be -2, isn't it? -2. It is in divided form, so it will go up, then it will be -2, and D, it is in terms of length. So we can write it like this. So we can write like this. Now it will become m mass to the power -1. Now L, there are 2 L, so it will be -2. It will go up there. There are 4 T, see, 2 T here and 2 T here. It will go up, it will be 4. So T to the power 4, and there are 2A, so A2. Okay, so this is the dimensional formula of capacitance. Okay, so this is the dimensional formula of capacitance. Now let's move ahead. If you know the formula, you know the dimension. That's the code for today. If you know the formula, you know the dimension. That's all. Okay, let's proceed ahead. Some constant have dimension. You need to know this. You might be thinking that constant, they do not have dimension. Simply we have this concept in our mind, but constant do have dimension. For example, this refractive index, both velocity upon velocity, so it will be cancelled, so there is no dimension. So this is a constant which has no dimension, but there are other constant which has dimension. For example, universal gas constant, it has dimension. See, it has dimension. So you need to mug up it, these constant have dimension, like Planck constant, Boltzmann constants, coefficient of viscosity. These have dimension. Now there are few set of physical quantities which have identical dimension, like acceleration, gravitational field strength, and acceleration due to gravity. Both of these are acceleration, isn't it? So they will have the same dimension. Same way, work, internal energy, potential energy, kinetic energy, torque, moment of force, couple, heat, light, work function, all, remember, all the energy will have same dimension. This dimension will work for all of this. Work and energy will have the same dimension. In the same way, you can go through it. Take the screenshot, you can go through it. Alright, let's move ahead. So these are the list I have made for you. You can go through it. Here are some interesting facts. This thing will have this capacitance and resistance. When you multiply capacitance and resistance, they will have the dimension of time. Similarly, when you divide the inductance and resistance, it will have the dimension of time. Let me prove to you this to you. See here, formula of capacitance is charge upon voltage, potential difference, isn't it? Similarly, formula of resistance, it's potential difference upon current. Okay, is it clear? So when we will multiply these two, it will be q by v into v by I, isn't it? V will be cancelled. Then what we get? Q equals to current into time, isn't it? It will be current will be cancelled. What we get is time. So when we multiply capacitance and resistance, we will get the dimension of time. Am I clear? Same is the case here when we will divide this inductance with resistance. See, formula for inductance is EMF by di upon dt. Okay, and resistance formula is V upon I. Now take it up, EMF into dt by di into I by V, isn't it? This will go up, it will get reversed. So this will cancel this. EMF and voltage both has the same unit, so it will be cancelled in terms of the dimension. Don't go for something else. Let's see in dimensional point of view here. This I and this I current will get cancelled. What we will get is time, so we will have the dimension of time. Am I clear? So go through it. These are also easy. When you will mug it off all, when you will know the formula, you know the dimension. This is simple. Hope all of your concepts are clear. In the coming days, I'll be uploading the similar contents. Please support my channel. Thank you for watching. Thank you very much.